So because some people were asking some questions about expanding capacity, I want to make sure we just go over it again one more time just to make sure everyone understands. If you already understand it, bear with me. If you're struggling a little bit, you're probably going to find this helpful. So first, let's see if I can find a nice working marker. I'm going to use my own. Okay. We're in a situation where we have our stack, but of course this isn't restricted to just a stack. This could be any sort of collection ADT I'm writing, where I want to use an array and then pretend that I've got this unlimited sized container. Even though deep down we all know that the array, we have that expand capacity thing, where we have to make a new array, but it's twice as big and copy things over. So here's our stack, and inside our stack we'll have like max value, I'll just count it as v, and maybe it's set to like 10 or something. And we have stack, I'll just draw as like that. The stack attribute really is just a pointer to an array, and the way we did it, 1, 2, 3, 4, let's make it 5 because I don't want to draw anymore. So that's our current situation, and maybe it's full. Inside here I have pointers to like the number 4, 6, 12, 1, and -7. Why? I don't know. It's arbitrary, it doesn't matter. That's my current situation. But of course, what's going to happen if I try to add a new thing? It's not going to work out very well because I'm out of room. So what we're going to do in this scenario is that add function is going to automatically call expand capacity for us. And then after expand capacity is done, add will operate just as it normally would. So expand capacity, what it does is it makes a new variable. Let's call it like new stack, NS for new stack. Okay? It's going to be a pointer to an array of the same type, which is going to be pointers to integers in our example that we were playing with before. So it's not that we're making, like this array right here, we're not making it bigger. This actual thing, it's stuck. It's as big as it's ever going to be. That's the way it is. What we're going to do is trick our program into thinking that it just kind of got bigger. Or trick the user, trick might not be the right word, but make it seem as if, oh, it's this array just arbitrarily growing for me. Or this container, because the array is not going to grow, but the container can because of expand capacity. And what we will do by convention, we're just going to double the size. So we'll make max size not 5 anymore, it'll be 10. There, now it fits in the box of the object. It's 10. So I'm going to make a new one. Great. That's our current situation. We made a new one. Yes?
What will be the value of SOAP when the array is full, stack is full for the first time?
Top here can still be 5.
5.
It'll be 5, but that was our check. If you remember at expand capacity, that if top was ever the same as max, which in this case max was 5 before I made it 10, and top, that's when I know I need to expand capacity. Then, once expand capacity is done, I can still add it to top, which is location 5, right? Because I will have the row. But back to expand capacity. Good question, though. So I've got this new array, but of course, I need to move the contents into here from here. Well, what are the contents integer pointers? Well, I'll just do a loop for ever how many things are in here, and copy over the contents. What is the contents in here? Someone yell it out. What? A pointer. Not 4. Gotcha. It's a pointer. So I copy over it's just a memory address to where this is, so I'll represent that with an arrow. Copy this over, copy this over, copy this over, copy this over, copy this over. Great. So now we have this new array here. We copied over the contents from the old one into here, and we're all good. Now we want to be good with our memory. So we will now want to delete this, the stack, the attribute stack. But remember, when we delete something like that, we're not deleting this. We're deleting what it's pointing to, the thing that was created in dynamic RAM. So this disappears. So immediately after I've deleted it, this pointer is pointing to like nothing. But of course, this attribute needs to be the attribute that gets us to that array. Currently, this random local variable inside the expand capacity function is the thing that gets us to that array. So here's what I'm going to do. I'm going to copy over the contents of this. What's the contents of underscore ns?
Pointers to functions.
Perfect. It's a pointer to our integer pointers, our array. So I'll copy over the contents, just a memory address. So this doesn't point here anymore. This points to the same thing. This function ends. This local variable disappears. But this still gets us to that memory address. Span capacity. It might be difficult to wrap your brain around at first, but it's clever because now it gives us the ability to automatically make our array bigger, even though the array never actually changed size. Just we made a new one and made the pointer point to the new one where we copied things over. Any last questions about expand capacity? Yes?
Should the new array be the continuous stack of that capacity, or can it be like 5 in one place or 3 in one place? And
Say that again, sorry?
The new array, as we are expanding it to 10, should it be the continuous stack, or can it be in pieces of 5, 3, or 2? Is there any way that is this possible?
Like, do you mean, I usually always just double it. Right? That's typically what I would do, and I would want to make it so that still fills left to right. Maybe I didn't understand your question.
I was asking if it should be continuous stack, or can it be in separate parts?
Oh, I mean, we could do it in a way if we wanted to get clever, but typically we want to have just one big, long array for simplicity. But you could do that. I mean, there's no rule against it. I wouldn't do it, though. Cool. Any other questions? Yeah?
Would it be better to just make your original max size bigger to avoid having like the work we do grow? Like if you have an original max that's really low, then it has to expand capacity a lot, doesn't that make the complexity overall worse? Like would it be better to have a max size that's pretty big, like 20 or 50, so that you don't have to call expand capacity as much?
Well, so let's break that question down because there's a lot to that question. The first part is like, what would it improve computational complexity? Well, really because of amortization, no, it's not. It would be the same. Because we amortize it, it really doesn't matter. In practice, we all know that there's that extra little bit of overhead though. Right? So we'll be aware of that. A lot of times when we're doing a lot of this data processing stuff, maybe we don't know what n is. If I am the programmer and I know what the size of my stack is going to be, if I know like, at most there will be 100 things in it, I'll create a stack with the constructor where I can pass it the size, and I'll say 100. But there's a lot of times I might not know. I'm writing a general purpose stack, right? I wrote a stack. Everybody in this room is going to take my code for a stack and use it for however they want it. I don't know what you want to do. I don't know if you want to read a file with 10 things in it, or if you want to read a file with 10 billion things in it. Maybe you don't even know, as the user. You're going to get an online stream of data. So I could make the decision, well, I'll just make max array arbitrarily large, and then I won't have that. But of course, now I've used up a lot of space. So there's always this trade-off. In that sense, a lot of times, there's a big theme we're going to see in class. We'll see trade-offs in terms of time complexity and space. Oh, this algorithm is faster, but it takes up a lot of space. An arbitrarily large amount of space, maybe even too. That can be a bad thing. So that idea, absolutely workable in a lot of situations. If you know, put it in that end, so you don't have to worry about expand capacity. Any other questions? I think I saw another hand. We're good? Okay. So now we're going going to talk about nodes and links. And we're going to create linked structures. A lot of places you will find what we're about to talk about called a linked list. But that's actually not quite right in my opinion, because a linked list is actually something a little bit different that we're going to learn about in class. Right now, all I'm talking about is this idea of creating nodes and this idea of references to other nodes and whatnot, or pointers to other nodes and whatnot. Where's the eraser? So, before I even start with this, I'm going to emphasize something. What I'm about to show you is not a data structure. What I'm about to show you is going to be like this nodes and the links between them. It's going to be more similar to the idea of an array, like a container, than it is to some other data structure. You gotta be aware of this. There's nodes and links. It's going to be relatively simple, very lightweight, but later we'll be able to use them in places where maybe we would use an array. And we'll look at some pros and cons. Long story short, at this stage, remember, what I'm about to show you, it's not a new data structure. It's just another way to hold on to information. It's another simple container, like an array. All right. What are we going to learn? See a different container instead of just arrays. We're going to implement some nodes, specifically an integer pointer node. We're going to implement a series of linked nodes together and see how we can add and remove things from this linked structure, right? So, imagine for a second, let's go back like a week and a half ago. We were talking about the student class, right? And the student class had a couple of attributes. The student had an attribute like first name, last name, email address, student number, and current average, right? I think that was it. Did I miss anything? Now remember, I could add whatever attributes I want. I'm inventing a student object. I can make whatever I want. And each of those each of those attributes, it doesn't really matter what type they are. I can make whatever I want. I'm the programmer. I get to invent it. So imagine for a second that my attribute is going to be, I'm going to make a new attribute called best friend. Okay? It's simple. It's just a best friend attribute, whatever that is. What it'll be is the type of the best friend attribute is going to be a pointer to another student object. Okay? So imagine for a second that, okay, you're going to be my student object. You've got a first name, last name, current average, all that stuff. But you also have this new attribute called best friend. And it's going to be a pointer to a student object. Some other student that exists in here. So pretend for a second that he's your best friend. Just point to him. And keep pointing. So that's the pointer. So I can ask you, remember I have getters and setters. Okay? Now before I do this, let's pretend, keep pointing, keep pointing. You also have a best friend. And it happens to not be you, sorry. It's not reciprocal. Your best friend is him. Point over there. And your best friend happens to be her. And your best friend happens to be him. Point really good. There we go. So just so everyone's aware, keep pointing. Don't stop pointing. You're involved, you're involved, you're involved, you're involved, and you are also involved, okay? So, here's what I could do. Let's say I have access to you. You're that student. You have a first name, okay? So I could be like, hey, what's your first name?
Ryan.
There you go, Ryan. Then I say, okay, Ryan, actually, so I said like, get first name in that case. I use the getter. Now I'm going to use another getter that says, hey, get best friend. There. You return the pointer to him. So now I know you. I could say, you get best friend. It gets me you. And then I can ask you, what's your best friend? What's your best friend? What's your best friend? What's your name? So I could say, you get best friend, get best friend, get best friend, get best friend, get first name. And suddenly I have this way to kind of traverse this series of friends. Interesting. Yeah.
So, like if you were
It'll be similar in that sense, yes. Very similar. Very, very, very similar. It's a very specific version of a graph. A graph is a much more general version of what I was just talking about. But anyways. Understand too that what we're just describing here is kind of a very mathematical idea, even though it might not seem like it, but it is. Anyways, so, warning, we're not defining a new abstract data type yet, we're just prepping to be able to start implementing abstract data types as something other than just an array. I already said this, gotta hammer it out. So, what's great about an array? Well, you know, contiguous pieces of RAM, they're fast, easy to allocate, you kind of get them for free. But what are some of the limitations? Well, they have a fixed size. I mean, we can expand capacity, right? We just learned that. So although arrays has fixed size, we kind of know of a roundabout way to expand capacity. But the reality is it still has a fixed size. And adding and removing things might require a lot of shifting around. So when we did the stack, for example, we didn't have to do a lot of shifting around because all the action happened at one end. But imagine I didn't have a stack, I had just some array, right? And it was just holding on to some specific information and I wanted to remove something from the center of that array. I'm gonna have to shift things around, right? It's kind of a pain. I'm gonna have to do it though. And the array has to be a contiguous chunk of RAM. I mean, maybe this is a couple decades ago and I say, hey, give me an array of size 1,000. And the computer's just like, I don't have that much space. I don't have a contiguous chunk of 1,000 amount for an integer. So now we're going to have these link structures consisting of things linked together, like a series of friends that kind of are linked in some way. We're going to do this with pointers. We love pointers. We can use this idea to implement a lot of really interesting, I don't want to say more advanced, and you don't need these data structures. You don't need link structures to do this, but it makes it pretty easy to. And we're going to focus, for the sake of right now, on what we would call a singly linked structure. It's just a series of things where each friend only has one best friend. That's it. It only has one pointer to another friend. We could have it have doubly linked where they point to each other and they could have multiple pointers, or we could have arbitrarily large number of pointers as well, which might give us something like a graph, like Matt was saying. But here we go. Here's an idea. I've got this pointer. It's a pointer to a type of object that we're going to typically call a node. We're going to create nodes, and nodes are going to hold on to two pieces of information typically. The node will hold on to some data, and also a node will also have a pointer to the subsequent node. Right? So this is a node. It currently holds on to the value, I don't know, is that teal? Looks like teal, right? Then it's off-white, beige, blue, and then black. But in addition to having that color, each node also has a pointer to the next one. Imagine this was an array for a second. Just think of this, but just smush it together, get rid of those little arrows. An array it's the same idea, right? It's the same idea in the sense that it's just holding on to information. But arrays, because arrays come in contiguous RAM, I don't need to do anything fancy to get to the subsequent thing, right? I just say, okay, go to the next memory location. Increase the index. There, I'm at the next one. These link structures don't work that way. If I want to get to the next one, there's no such thing as increasing an index. I have to follow the pointer to the memory address where the next container is. Yes?
So does that mean that you don't have to allocate a chunk of continuous amount of RAM?
They could be everywhere, just like those friends. Imagine you were the student objects in RAM. But you were pointing there, you pointed there, you pointed there, you pointed there. They could be anywhere. It doesn't matter. I mean, they're going to be in dynamic RAM if we're doing them dynamically allocated, but they could be anywhere in there. So these are what we call nodes, and the little arrows we'll call the pointers. And note, head, what is head? It's a pointer to what? It's a pointer to the first node. A lot of people, this right here, listen up. This head tends to confuse a lot of people when they're getting started. People think like, okay, so head's like a special node that points to the head of the node. No, absolutely not. Head is a pointer that gets us to the beginning. So head is not a node. Head is a pointer to a node. That teal one, that's the actual first part of our container, of our linked structure. Any questions? Okay. More pointers to nodes, yeah. The reason we like this, as someone just pointed out, is these things can be anywhere in RAM. They don't need to be in a contiguous chunk of RAM. That's handy, that's cool. And it actually allows us to quickly insert and remove things really quickly without having to shift anything around. I'll show you examples of that soon. It's pretty cool. And they don't have a fixed size. There's nothing stopping you where I ask, okay, what's your best friend? And you don't have one. And then later I'll be like, okay, you set your best friend to her. Right? Like I can do that. And now suddenly that container just got larger. I don't have to expand an array's capacity or anything. I just set you pointing to another node or a student. So how do we do this? Well, let's have a quick look at an implementation. First, we got to start with a node. The node class is going to be our basic definition of how to create these linked structures. So a linked structure is just a sequence of these nodes that point to their successors. A singly linked structure. We can have doubly linked ones where they can point back, but we're not talking about those right now. A node is a singly linked structure, typically has two attributes only. The data, that was like your first name, and a pointer. So again, the data, when comparing these linked structures to arrays, the data attribute of the node, the information that it's holding, is analogous to the contents of the array at a specific location. Where arrays don't really have this next node, like I was just saying, because you just go to the next place in RAM where the next thing would be. You just increment that index, and you're good to go. So here we go. This is what it would look like, right? A lot of times we'll draw these things this way, where you've got, okay, each node is kind of divided into two parts. The first part is the data, the contents that that node is holding, and the pointer pointing to where the next node is. Yeah?
If you were to remove a piece of data, would you just modify the pointer on the data before it? Like, it's like to point around it instead?
Hold on to that question because I have a feeling we might get to it. Because I'm not 100% sure what you mean, but I have a feeling once we finish the lecture, we're going to answer a lot of questions like that. If not, ask again at the end and we'll clear it up. Anything else? Yeah?
Do they have to have the same data type, all the nodes?
So, no, because there are ways around that, but typically they would be holding all the same data type. But we're going to learn about something called like inheritance and whatnot later on, and in different programming languages it doesn't care so much. For our purposes, yeah, they're going to be all the same type. Yeah?
Like, if they're pointing to something, like the type of that pointer, could it be just like nothing until you have something to make it point to?
The type of the pointer, so because we have a series of node objects, the type of those pointers are going to be pointers to node objects. But the value, so the type, we're going to learn a little bit about something called generics very soon. Which, once we learn about that, you could kind of throw away what I'm about to say. But, if I'm making an integer node, okay, the data inside the integer node is always going to be an integer. Or maybe, sorry, an integer pointer, because I like pointers. And the type of the pointer, the type of the next one, no matter what, is always going to be a pointer to an integer node. It will be. Now, Whether or not that pointer actually has a value doesn't matter yet. It'll either point to an integer node or maybe null. Sit tight, I think we're going to answer that in like 2 seconds. Good question though. Your head's in the right place. Any other questions? I love teaching these link structures. They're a lot of fun. You have a question?
No, actually it holds data and as well as a pointer.
Yeah.
So what would be the last one?
The last one, it points to null. In fact, there you go.
Okay.
The last one would typically point to nothing. Null is a special word we'll use in computer science that means nothing. It's a special value that could be useful. I have a pointer, and I can ask the question, is this pointer pointing to something useful or not? And I can say, hey, are you pointing, if you program everything really nicely, I can say, are you pointing to null? And if the answer is yes, I know I'm at the end of the list. Or pardon me, the end of this series of things, right? But if it's not null, then I know there's more to go, and I can just keep going. So if I wanted to perhaps iterate through this thing, I could start at the head and be like, okay, is the next null? No? Go to the next. Is the next null? No? Go to the next. Is the next null? Yes. Oh, I'm done. We'll see an example of that again in a moment. Look at this. You're all asking questions. Your head's in the right place. Yeah?
So like when it comes to a null pointer, like say you have a pointer pointing to a memory location that nothing is in, is that considered null pointer as well or no? So
say that again?
If you have a pointer pointing to a memory location but there's nothing there, is that a null pointer?
No, it's not.
Okay.
Null pointer in C++, I'm not 100% sure. I'm pretty sure in C++, null pointer points to memory address like 0. That might not be right. It might be null, which is a slightly different thing that means 0. I can't remember, but it's a special value. So if there's nothing there, it doesn't mean null. It's just a series of zeros and ones. Yeah?
Could you have the last node point back to the first one?
You can have that last node point wherever you want.
Okay.
But of course, if it pointed back to the first, and I was doing that iterating thing, I would go around forever. All right? So let's start implementing this. Let's start with the header. There. It's going to be an integer pointer node. So the data is going to be an integer pointer. And next is going to be an int node pointer. Great. That's it. It's going to be a pointer to something of the same type. Right? Cool? So, what do we want? Well, let's throw our constructors and deconstructors in there like good programmers. Maybe int node will have some default values. Another one that takes a pointer to an integer to actually set that data, okay? A copy constructor and a deconstructor. And we'll have our getters and setters. That's it. That's literally it. It's that simple. This is a very simple class. That's it. All this thing needs to do is hold on to that information, and then the getters and setters. In fact, because it's so simple, a lot of people, when implementing this, they'll even make the attributes public, just so you don't even need the getters and setters. It makes things even easier. We'll do it with the getters and setters just because, but it's actually not uncommon to see it public, because it's just that simple. Yeah?
So the data there, it's not actually, like it's a pointer to it. It's not going to be in the node, right?
It's going to be a pointer to some integer somewhere. That's it. I could have made it integer if I wanted. I like pointers instead. So we're going to make it an integer pointer. Ultimately, that could be anything I want. If I want the data to be another integer pointer, or pardon me, another int node, I could do that. It would be weird, I guess, because you'd end up with this like two-dimensional thing. But anyways.
So you said if you made the attributes public, it would get rid of the getters and setters. Can you just explain that a little bit? Like how that would actually get rid of them?
So I wouldn't need them anymore. Because they're public, that means I can then access those attributes, modify and access them anywhere else for free. I don't need to go through the gatekeepers out of the getters and setters. Okay. But because they're private here, that's why we need those getters and setters. If they're public, don't need them anymore, anyone can access them. Yeah. Yeah?
I'm having a hard time understanding
So the class name is just like the type, right? So remember in the lab when you were doing, or in the slides a couple weeks ago when we were doing that course class, right? And I had that array. The contents of that array were student pointers. I defined the student class. And once it's defined, C++ will let me use it based on how it's defined. And that means I can create a variable of type student, or I can create a variable of type student pointer and have a student there. So here, I'm saying, oh, okay, I want next to be an attribute, but it's going to be of type int node pointer. So all it's going to be is a pointer to something that must be an integer node. If we go back here, let's just look at this picture again. Head, in this case, head, assuming that this is an integer point or an integer node, head is a pointer to an integer node, right? In the same sense that I can say student star s equals new I can write that, right? Student pointer s equals a new student. It'll go create a new student. S is now pointing to that student object. Been doing this for weeks. We can do this. This would be like head, right? I want head. Oop, no. Ignore that. Node. Star. Let's call it head. Equals a new, assuming it's written, int node. And maybe I'd give it, and forget it, I just called the default one. There. So that's what I would write if I wanted this, to start with head. But of course, head is now pointing to a new node, but that new node here, it's pretty empty. There's no next in it. There's no data there. So I would have to modify it. Now, head then is a pointer to that first box on the left. And it has two pieces of information. Data, which in our case is a pointer to an integer. So if I said, hey data, give me your data, and it would be the memory address of what's in that variable. But I also have another pointer, or another attribute, that's a pointer to type thing that's of type integer pointer. Meaning that that attribute, just like in the exact same way that in our case of integer pointers, in the int node, data must be pointing to something that is an integer. Like data must contain an integer pointer. Next must contain the memory address of an int node. That's all it means. Don't think too hard. Just look at what the code says. Oh, it must be pointing to something of the same type. I think as we go, it might become a little clearer too. Just chew on it slowly and don't skip too many steps. Yeah.
For the void function set next, are we setting the memory address of the next node that's pointing to, or the data that the next?
Here, but what do you think?
Well, it takes a pointer as an argument, so I imagine it's probably setting the value of the next one.
Well, okay, be more specific. The value of the next one. All this does is modify the attribute next. I mean, we haven't looked at the code yet, so how would you know? But getters and setters, you should know that all it's going to do is say like, okay, underscore next equals n. That's all the set next is going to be.
Oh, okay.
Well, you'll see. All right. So let me ask you something. If I have head, if all I have access to is head, how do I access the first one's data? Like, what code would I type? Okay, dereference head, and then what?
Use the get data function.
Call get data. And I'll probably have to dereference that too, because get data is a pointer. I'll return an integer pointer. Say that again. Head is a pointer. So I'll have to dereference head, or I can say head, then like that, like dash, greater than, that little arrow, right? And that when I do that, it'll get me to like like what it is. Well, it's that node. And then if I want to get something from that node, what are the 4 methods I have for that node? Get data, set data, get next, set next. I want to get the data. So I would be like, okay, head, arrow, get data. And that'll return the data from the first node. What if I wanted the data from the second one? Take a second, think about it. Just generalize what I said before. Who wants to take a guess? Not you. Somebody else. Someone's got to take a guess. What do you say?
Get next.
So, like, you're on to something, but let's get a little bit more complete. Head. Get next. Get data.
Get data.
So you get the next one, which is a pointer to the next node, but then you want to get the data from that node. So I would say head, next, get data. Head, get next, get data. What if I wanted stuff from that last one? Now you better know. No?
Head, get next, get next,
Get next.
Yeah. Who said that? Yeah. Head, get next,
Get next.
get next,
Get data.
get data. We're set. What happens if there was 100 things in there? How many get next would I need?
99.
A lot. 99, 100, whatever. A lot. Yeah.
Could you also use pointer arithmetic to get to the next one, or
Well, no, because you don't know.
you don't know?
Like, you don't know where that pointer is, right? So pointer arithmetic works in arrays because you know that the next thing must be some number of, like, memory addresses down the line. Here, this could be anywhere in RAM. I don't know where it is. How do we get a node's predecessor? I'll give you a second to think about this. Pardon? That never existed. You're cheating.
Can you just do like one last get next than you did before?
Interesting. So, the answer to this question is, well, you can't. If I'm at a given node, it's impossible for me to move. All I can do is ever get to the successor. I can never get to the predecessor. That's against the rules. But you are 100% correct. Here's what you could do. If I have a pointer to the node I want to get the one before. So imagine I'm at the last node. Okay? I have a pointer to that last node. And how did I get there? Well, I've got, like, I went through and I'm just like, okay, head, next, next. Okay, great. I've got a pointer to that node. And if I want the preceding one, what I can do is I can just loop, start at the head, and move on down until the next node is the one I'm pointing at. We're going to see an example of this as we go on, but you're absolutely right. I tried to trick you, but you're too smart. Well done. How is this different from an array? Well, it's very different. How do we add something to this list? I say list, it's not really a list, it's a series of nodes. How would I add something? Take a second, think about this. Let's say I have a pointer that happens to be pointing to that last node. How do I add a node to that list? Put your hand in. Well, we can't use get next. Oh, whoa, wait, hold on. So if I have a pointer to the last node, you're saying set next. Set next to what? A new what?
Set data,
Set
no,
node.
right?
No, assume data's already there.
Oh, then set next to
To what? A new pointer to what? Create a new node, or maybe the node already exists, I guess. But you will say set next to the node you want to come after. You have a question?
I was going to ask if it would be expand
Nope, we don't need expand capacity because I could always be at the end and be like, set your next to another node. Set your next to another node. And set your next to another node. Is there a limit to the number of things I could ever keep appending to the end of this series of list linked nodes? In theory, it could go on forever. In practice, all right, eventually we're going to run out of the RAM, I guess, right? But in theory, I could just keep adding things. It doesn't matter. Allocate a little RAM over there, a little RAM over there, a little over there, a little over there, a little. It doesn't matter. I'm bouncing all over the place, getting the next ones, but I can go on forever. How would I add something to the front of this list? Just take a second, think about this. Don't say it out loud. Just give yourself a minute, think about it. How about this? I create a new node that I want to be the new head. That new node, what should that new node's next become?
First head one. First.
Head. Then what do I want to set head to?
Next.
The new node I just created. Because remember, head is not a node. Head is a pointer to the node that happens to be at the beginning. We're going to go over all these examples a lot. But last, any idea on how I would insert a node somewhere into the middle of this list? I'm saying list. Maybe list isn't the right word. Into the middle of this linked structure. How would I do that? Don't tell me. It's a quick thought experiment. How would we remove something? From the beginning, middle, end. Change pointers. I like that idea. So we'll pick up here on Tuesday, but we'll have a lecture activity.